illustration is there. Great piece to know about. In the reviews this week, the week of the ending the 2nd or the 3rd, we talked about this graph a bit in the fact that this is the HIV viral life cycle. We have HIV out in the cells come up. We have the address label here, GP41 or GP120 attaching to CD4 using CCR5 initially as a co-receptor. Go back and review those because that's really important stuff to know, and we talked about that in the first review we did. We see fusion of the membrane, so the membranes are coming into contact, like to like, and then the address or the safe gets dumped off into the cytoplasm here. Once it does, everything gets dumped out, and see here's this reverse the RNA, the viral RNA, with all the proteins like reverse transcriptase. Then reverse transcriptase can turn that RNA into DNA, like we said, it has to be DNA in order to get into the host nucleus. So once it's copied, we have this DNA hanging out in the cytoplasm. It kind of naturally gets into the nucleus, and it's there that integrates. I don't think we have a piece for integrase, but just know that in the nucleus of the cell, not the cytoplasm, integrase is responsible for copying or for integrating the piece of DNA that we copied from RNA into the host genome or the host blueprint. From there, and don't worry too much about all this stuff here, but from there the host can then make copies based off the DNA of the virus. It makes new virus, which hangs out at the surface and then buds out. So the new virus actually buds out there. And here you see it's stealing the lipid bilayer, or the membrane, to form the outside of its envelope. So it has that lipid bilayer to protect it. And it actually kind of acts as a camouflage because it looks similar to the material that your cells have on the outside of it when it's out free-floating, right? Then it is not active. You have an inactive virus. Sean mentioned protease as an enzyme that's going to cut up those different pieces of a polyprotein that was created here by your ribosomes after the DNA was changed into mRNA and then used to make these proteins that HIV is going to use to form itself. Out here, outside the cell, is where the protease, which is the enzyme that is unique to HIV, cuts up these chains of protein and then organizes them to create a good save and to get everything going. Once that's going, you have an active viral particle. So once protease cleaves things up, your virus becomes active and able to infect. At that point, you express GP120 and GP41. Again, those are the address labels on the outside, and the cycle starts over again. So let's talk about some of those tools in a little more detail.
Okay, so we have our reverse transcriptase, again, viral RNA to DNA. Then we integrate the viral DNA into the host genome. We named a few tools. We did name a few tools, but for reverse transcriptase, the important thing about this tool is that it creates a high degree of high degree of mutation, a high degree of variation in between viruses. So we talked about in a previous, we're going to talk about the variety, or what do we call that? The phylogenetic variety in one person is greater than the variety of all the flu cells in the world. So the reason for the high mutation rate of HIV is because of the reverse transcriptase. And sometimes the virus gets a poor copy, which makes it die, and then other times it gets a copy that gives it an evolutionary advantageous advantage over the body's immune system. So reverse transcriptase, and again, this is a tool that it brings in, and it's a great target for drugs because you attack reverse transcriptase, the virus, but not the human body. So we can attack the reverse transcriptase with antiretroviral drugs, ARVs, and we briefly touched on this. We have the nucleoside reverse transcriptase inhibitors, NRTIs, which I think nukes, and then we have NRTIs, NNRTIs, non-nucleoside reverse transcriptase. So that's reverse transcriptase, yeah, Justin?
Yeah, so Sean mentioned that there are mistakes made, spelled mistakes. Check out how Dr. Jacob spelled that, it's been fun. with reverse transcriptase that cause for mutations, and this allows it to evade treatment. Like Sean said, we have NRTIs that specifically target viral enzymes. So reverse transcriptase is one of those things, just to copy what Sean said, it's only in the virus. It's not in our human cells, so if we target it, it's not going to be as toxic, right, for our human cells. So we really want to target that. So we have these pieces called NRTIs. AZT is an example of the first NRTI that hit the market. So let's say this patient has HIV, they've got this viral load, you introduce HIV or AZT, and that causes further reduction in HIV replication. So you reduce the population, right? So this is the viral load in the blood. So over time, your viral load decreases because the medication's working. It's awesome. It comes down. But then the virus is tricky because there's so much mutation. One of the viruses is going to say, oh man, look, I have this way to evade AZT. Like, I'm no longer going to be affected by it. The fact that this is reduced is great, but it's because AZT is working. As soon as that virus is able to get away from the function of AZT, the mechanism, through that mutation that it has, it changes it physiologically, then it's going to start to replicate because it's uncontrolled, and the viral load's going to go right back up. So the problem with one drug is that HIV, because of the reverse transcriptase, is able to have so many different varieties of itself that you're going to find these that are able to mutate. So let's keep going. We're on low on time. This is a good example of an illustration of what it looks like when you have maybe a couple of viruses that are resistant, and it shows how the population is really limited through the use of pressure given by a drug, but as time goes on, they're going to be able to evade the effects of the drug. This is another example of that. This is a phylogenetic tree that Sean discussed. So this picture here is all the different varieties of the flu virus, right? In 1996. This is global. This is the picture. It kind of shows the same area. This is one individual with HIV, and this is 6 years after they were infected. So this is an individual who has as many varieties of HIV in their body as there are varieties of flu in the entire world. If you look at just a small, not so small, but a smaller area, like the Congo, right? Look at how much variety to the virus there is compared to that of global influenza. And that's an interesting bit to understand. Awesome. Another picture.
I think we're going to talk about the safe here.
Yeah, let's talk about the safe.
Great way to kill HIV. Okay, so the safe, is the safe made out of an oily membrane?
Yeah.
Okay, so how do you disperse oil? You use soap. It dissolves it.
Yeah.
Why
if you're healthy.
Yeah. So why can't we just drink soap to get rid of HIV? Because all of your human cells are made out of oil as well, oily membranes. And an important thing again about these HIV drugs is that they target the virus and not the human body. So with soap, you would kill everything. You kill the human and the virus. So we can't do that. So let's talk more about drugs that we can use then that won't attack the host.
Yeah.
With respect to the safe, again, the safe is made out of those proteins, the two protein components that originally start out as one protein. And then you have to cut this protein, viral protease cuts this protein, which then creates the safe around the blueprint and then also a structural component of the virus. Without this cut, you're not going to have active HIV. So protease is something, this viral protease is something that HIV brings. Yeah,
It encodes for
it. Encodes.
Yeah,
okay. It encodes for it, and so we can use protease inhibitors, which we have talked a little bit about in class. It's one of the standards of care in America, 2 NRTIs and 1 protease inhibitor.
Absolutely.
And so that's a great target, is the protease, to inhibit the protease. And, moving.
So what Sean mentioned too is viral protease, again, just to beat it a horse. This is very specific to the virus. It's not going to be in the host cell, so if you use protease, it's going to target that and be less toxic. So let's look past this picture, which we saw again.